And welcome again. This is some sort of explanation, not a problem exactly. And you have to just assume something. I'm trying to explain the solid angle. And you have to assume something first. There are two kinds of areas. This concept is given by the creators of this idea, solid angle. One is called closed surface, and another one is called open surface, like this surface of a disk, surface of a surface of that is not closed, is open. And you have to maintain one thing. You should think like in terms of patches, small surface areas. And when you will need to think about a finite area, you will automatically conceive the idea there what to do. So don't worry, just start thinking like this, that there is a small patch of area, call it ds, and just make one promise to yourself that once you identify the body of the area, you will draw an arrow perpendicular to it. Though you can draw perpendicular in any direction, you are free to draw perpendicular arrow in any direction, because an area, there will be always perpendiculars in both the directions, and you can take at your will. But in one problem, you should either call this outward normal and call this inward normal. In one problem, throughout the problem, you have to consider either outward normal or inward normal, not both in the same problem. So be consistent in taking the direction of normal, that is perpendicular to the body of the patches, a small infinitesimal area vectors. And this is the body of the area vector, surface, and this is its direction. And body and surfaces are always perpendicular to each other. So you can see here is an area ds, and its body is like this. Body is perpendicular to its arrow, right? And this is perhaps this surface area is perpendicular to its, so its arrow is in this direction and its body is perpendicular to the arrow. So you have to make just two commitments to yourself. You will either choose an outward normal in a closed surface especially, or an inward normal, to draw the direction of a small patch of area, infinitesimal area. And second thing is that the body of the area, the surface, it representing the area vector, infinitesimal area vector, and its arrow, the direction of the area vector, should be perpendicular to each other. And that's all. Though this is a scalar quantity, but it has some sense like electric current. And this is simply defined as, this thing is called omega. D omega is equal to ds, the area vector, dot product of the position vector, where it is position vector is drawn with respect to the point with respect to which it is subtending a solid angle, divided by r cube. So the numerator can be written as ds. Suppose the angle between r and ds is theta, then you will be calling it ds cos theta multiplied by r cube. That comes like ds cos theta multiplied by r square. So it is dimensionless. And dividing, perhaps we divide by r square to make it dimensionless. So this is a common pattern to make angles dimensionless. So its unit is steradian, though it's dimensionless, but it has got an unit. Plane area is radian and this is steradian. And now we come to the thing. So what is the d sigma subtended? D sigma is this in this case, because by definition ds is here, r is here, so ds cos theta will be, the arrow of ds cos theta will be always in the direction of this position vector. You can see here. And so the body of ds cos theta will be perpendicular to the r vector always. So you will have to take this r length and the area of the body that is perpendicular to the r. Surface area should be perpendicular to the arrow of r vector. And this is simple. Maybe you would like to know where is ds sine theta in this case. So this is dr, this is ds cos theta. Ds sine theta will be something like this, ds sine theta. And what will be the body of ds sine theta? It might be like this. Ds sine theta will be this. And it does not contribute in terms of its body is parallel to the vector r, position vector. That means it is not going to contribute any solid angle at point 2. So because its direction is here and it is perpendicular to r, so theoretically it cannot produce any solid angle at point 2. So you need to understand these things, and then we move to another problem that is the part of this explanation. Here is the part. Suppose S is the unit surface centered. Unit surface means surface area of a unit sphere. Surface area of a sphere of radius 1 unit. That is what I am calling it, a unit surface. And what is the solid angle sigma subtended by S at O? This is quite simple. You can take a sphere of radius 1, or if you want you can take a sphere of radius r as well, and then consider patches on the surfaces of this small infinitesimal areas at the surface of this sphere. And since bodies are perpendicular to this radius, because these are small, infinitesimally small, so these bodies are basically creating a cone at point 2, and it's a right circular cone, and its base is perpendicular to the radius, so that you can write ds vector either in terms of in the direction of outward normal or inside normal. I chose the outside normal. People usually choose it, so I chose it. And this is your r vector in the same direction. And its magnitude of r vector is capital R, as you can see here. And this is our r vector. So ds and r vector has zero angle between them. That means they are along the same direction. So d sigma here you can write is simply ds upon r square, and ds is nothing but ds upon r square. Yes, magnitude of vector r is r, so you can write like this. And so d sigma is ds. So if you want to find the sigma, you need to integrate this d sigma, and this circle represents that we are working with a closed surface, nothing else. So this integration of d sigma will be 1 by 1 upon r square ds, And you can see, you always know that this closed surface area ds will be equal to 4 pi r square. This is the surface area of this sphere, and you will get your result as 4 pi. Or if you don't want to bother about these things, you can simply write, in case of spherical surfaces, you can simply write what will be the solid angle subtended by a spherical surface, and your answer will be surface area divided by the radius squared, and you will get your value as 4 pi. Though there is one thing that I would like to attract your attention is this second part of the problem. This is basically the operational part of the solid angle, and it says suppose S is a closed surface of an arbitrary shape. Prove that it will to subtend a total angle of 4 pi at an inside point if O lies inside S. So O is the inside point, and so it should not be a sphere, and should not O cannot only be the center of the sphere. It can be any point inside this arbitrary shaped surface you can see in this picture, and the total solid angle subtended by this arbitrary surface at any point O inside it will be equal to 4 pi. This is the first part of the problem, and I have drawn a picture, and this picture is a smart picture, because this picture strongly suggests that I have chosen an origin, and I have chosen a unit sphere, a sphere of unit radius inside this arbitrary shaped closed surface, and I have made a cone like this, and you can see that area element, this area element DAA, this subtends the same solid angle at point O, that is subtended by DAB, that is, and the area element at the surface of this unit sphere. And I'm thinking like this is going to be true for all the other cones. You can take it here, and the surface area is this, but you will need the surface, the component of this surface area, like perpendicular in the radial direction, so that it's in the component of this area vector, and this is going to subtend the same solid angle here. And if I call this d sigma 2, then sigma will be simply the sum of omega will be the sum of d omega 1 plus d omega 2, and finally you are going to get the 4 pi, because this is the sphere and this is the center of the sphere. So the sphere is going to submit a total solid angle of 4 pi at its center, and by this we know now that any closed surface of any shape at any inside point it is going to subtend a total solid angle of 4 pi, nothing else. This is the first of the results. And the second result is suppose S is a closed surface of arbitrary shape, then it subtends a total solid angle 0 at a point O that lies outside this closed surface. And for this is the figure. I have again taken a point O outside the closed surface, and I have taken I tried to make two cones, and I know at this point O the solid angle subtended by the real solid angle is going to be subtended by the base of this cone at here, and by this the cone of this base, and these are quite a small, the distances you might want to ignore, and this surface area is going to subtend both the solid angles. So this and this solid angle, both solid angle are same in magnitude, but there is one thing: this solid angle is negative and this solid angle is positive, because you are going to draw a position vector. If I can, like this, then here the angle is, acute, and here the angle is obtuse. So this solid angle is going to be plus and this solid angle is going to be minus, and so the net solid angle subtended by these two surfaces at point A will become equal to 0. And this is true for all other cones, and in this case we will always get a solid angle, total solid angle 0. So these are the facts related with solid angle. This is a quite simple idea. You have to just keep two things in mind and you will be ready to go. Thank you very much for watching.